Okay, so now what's the relevant input for learning this target knowledge of syntactic islands, right? What part of the input should we be looking at? And of course, this depends on how we think children learn it. That is, what is the learning theory that transforms that input into the knowledge needed to produce the observable output, right? And so in 2013, Pearl and Sprouse had the following intuitions, which is simply, if you are a learner, if you are a child, learn what you can from the dependencies you do actually observe in your input, and then apply that learned knowledge, whatever form it takes, to make a judgment about dependencies you haven't seen before, like, for example, syntactic islands, and maybe other longer dependencies, or maybe just dependencies you haven't seen before, like the stimuli from the acceptability judgment study, for example. So this is the concrete learning strategy that Pearl and Sprouse 2013 came up with. Want to view WH dependencies in terms of their building blocks, right? And track those building blocks in the input. That's the relevant part of the input. So let's be more precise about what this looks like. So the dependencies here are going to be represented as a sequence of what we called container nodes. That is, what phrases contain the gap. So here's our gap. So the phrase is, this phrase contains it, and then this phrase contains that one, but not the WH word, right? So we're not going to include that one. So the sequence of container nodes is, the sequence of phrases that contain the gap, but not the WH word. So here we have a matrix clause object. What did you see? And we can represent that, we can characterize it in the following way. So we begin, start, and end are sort of our markers of this dependency's beginning and ending. And then it's the IP and the VP that are the container node sequence. So start, IP, VP, end represents our matrix clause object dependency, like what did you see? And of course you can do this for all kinds of dependencies. So for a simple matrix clause subject, like what happened, we can represent that as start, IP, end, right? That's the sequence of phrases that contain the gap, but not the WH word. We can of course do this for longer dependencies like this one. What did she want to do? Where we have an embedded non-finite object down here, right? So we have our gap and then VP, IP, VP, IP. Okay, so that's the sequence that we're capturing with our container node sequence. So start, IP, VP, IP, VP, IP, VP, IP, VP, end, right? And then we can also, of course, do this for any dependency, including ungrammatical dependencies. And in particular, here we have, who did Lily think the kitty for was pretty? Here's our ungrammatical dependency. And we characterize it again by the phrases that contain the gap, right, but not the WH word. So we have start, IP, VP, CP, that, IP, NP, PB, right? And the idea is that these ungrammatical dependencies are going to have low probability segments, one or more of these chunks that are bad, right? And so if children break these dependencies into smaller building blocks, they can identify if a dependency has one or more bad segments made up of one or more low probability building blocks, right? So the building blocks, what we're going to call them are syntactic trigrams, but they're just trigrams of our container nodes. So if we have a container node sequence like this one from our matrix clause object, like what did you see, start, IP, VP, end, we just break them up into a moving window of 3. So start, IP, VP is one building block, IP, VP, end is the second building block, and these can be recombined, right, to recreate the original dependency. These are our building blocks, our syntactic trigrams. Right? And we can do this for, any dependency we like. Right here we have the longer one. It includes our 2 building blocks from before and 2 additional ones that capture that internal segment. We can do it, of course, for our shortest dependency, which is just one start, IP, end for the matrix subject, like what happened. And of course we can do it for our longer, in this case, island crossing dependency, which is going to use some of our good building blocks, but also is going to include some building blocks for what we think is the bad segment, more or less. So here's the strategy. You have all these building blocks, right? And what you're going to do as a child is track the relative frequency of the syntactic trigrams in your input, right? You're going to have input, it's going to have a bunch of dependencies, you're going to break them up into these building blocks, and you're just going to basically count how often they occur, right? And of course, some of them are going to be more common, they're going to occur a lot, and some of them aren't, they're going to occur less, right? I represented that here with size, right? So these occur a lot, these don't occur a lot, but they're there, right? And then some of them, like these guys, are never going to occur at all in your input. The building block's just not there, okay? So what we're then going to use, the important number, so to speak, is the relative syntactic trigram frequency. It's our trigram, the probability of that trigram. And it's basically a smooth version of the number of that trigram over the total number, right? And the reason it's smoothed is so that you don't actually end up with zero probability for things that occur 0 times. They get an eensy-weensy bit of probability, right? But in general, everything is, very similar to the relative frequency in the input. That's your relative syntactic trigram frequency. That's your basic number. So any WH dependency can then be constructed from its syntactic trigram building blocks, right? So for example, the way that we did it in Pearl and Sprouse 2013 was just to take the product of those individual building block probabilities, right? Just multiply them together. So start IPVP times IPVPN's probability will give you back the reconstructed probability for this entire sequence, start IPVPN. And you can do this for any sequence you like, right? For the longer sequence, maybe it'll have, again, our 2 frequent building blocks, or some less frequent building blocks are in there. And of course, for our island crossing dependency, right, it'll include building blocks that were never seen. So they have probabilities that are just a titch above 0, right? But they're really low, right? And so just as a quick note, this, again, we did this by taking the product of the probabilities. You can aggregate these probabilities any way you like, a number of different options, but this was the way that we did it in Pearl and Sprouse 2013, and it worked out great. So that's, one way to go. So then, a WH dependency's probability, right, that product there, can stand in for its judged acceptability, that measurable outcome that we have data for, right? And so in particular, lower probability dependencies are dispreferred compared to higher probability dependencies. That's what we're looking for.